Buenos dias. I would like to thank you, Juan Carlo, for your kind introduction and for organizing this ninth World Cherry meeting, and also for inviting me to make this presentation on soil moisture monitoring and irrigation management. We need to irrigate to provide adequate water to prevent plant stress, maximize yield, and to improve fruit quality. This can be more of a challenge in high-density plantings where roots are restricted, such as when we're using rootstocks like GI3. Irrigation replaces the water loss from evapotranspiration. Evaporation occurs at the soil and leaf surfaces, and transpiration occurs when the stomates open to acquire CO2 for growth. Dry soil and water stress could cause the stomates to close, and therefore resulting in lower growth. High temperatures and wind increase evapotranspiration. Water potential drives the movement of water from the soil through the plant to the atmosphere. It is the energy required to move the water from place to place. It is measured as a negative value, negative megapascals, and less negative values are wetter than more negative values. Water moves from wetter to drier sites. The atmosphere has the most negative water potentials, and this is what drives the movement of water through the soil, to the plant, through the plant, to the atmosphere as transpiration when the leaf stomates are open. To meet these water demands, we need well-designed irrigation systems that can meet peak flow requirements, which use efficient irrigation technologies such as drip or microsprinkler, and that can be fully or semi-automated to respond to sensors for irrigation scheduling. Irrigation zones should be designed so that the maximum runtime will meet peak water demand requirements, and so that the runtime can be adjusted to reduce application rates indicated by irrigation scheduling calculations. Irrigation scheduling tells us when and how much water to apply. I will discuss two methods. The first is based on soil moisture monitoring, and the second on weather data or climate monitoring. The main focus of this talk will be on soil monitoring as requested by the organizers of this meeting. There are two types of soil moisture monitoring used in irrigation management: soil moisture potential and soil moisture content. I described water potential earlier. Soil water potential is a measure of the force with which water is held by the soil particles and in the pores. It is used to define which soil water is available to plants. It is measured as negative megapascals or kilopascals. It is also called soil water tension, which is usually measured in bars or centibars, which are positive values. 1 megapascal equals 10 bars and 1 kilopascal equals 1 centibar. As mentioned earlier, water moves to roots in response to potential differences. Soil water content, on the other hand, is the amount of water in the soil and is measured as the percentage of the soil. This can be either as a weight or a volume, but it is usually reported as volumetric soil water percentage or water content for irrigation purposes. The two types of measurement are related. Looking at the graph, we can see that at the same water potential, this is on the horizontal axis, that different types of soils hold different amount of water, or they have different water contents as measured on the vertical axis. This is important because plant roots can only access water between certain water potentials. For example, between minus 0.03 megapascals, which is called field capacity, and minus 1.5 megapascals, which is called permanent wilting point, And this really applies to fine textured and medium textured soils. For coarse textured soils, there is much less water content as the water potential becomes more and more dry. So we usually consider that the available water is between minus 0.01 megapascals and minus 0.1 megapascals. And this is because the movement of water through the soil is hampered by the very low water content in these coarse textured soils. When water is added to the soil, it first saturates the soil and then rapidly drains away. And this rapidly draining water cannot be readily accessed by plant roots. Available water storage capacity is the amount of water that is stored in the soil that is available to plants. This is an important property for irrigation scheduling, especially if the soil is going to be used as a reservoir between irrigations. This is characteristic of high pressure impact sprinkler irrigation systems, where water is applied at a greater than 3-day interval and the soil is allowed to dry down between irrigations. For micro irrigation, it is less important to consider as high frequency applications, less than 3-day intervals, made in response to scheduling, keep soil moisture levels high in the root zone. Finally, there is some water that is held below minus 1.5 megapascals, considered to be bound water, which is not available to the plants that we grow. Available water storage capacity varies with soil type, crop rooting depth, and density. It is often reported as a depth of water, for example, centimeters, to match rainfall and irrigation applications, which has traditionally been reported as depths. In 1 meter of soil, we can expect different amounts of water storage capacity for different soil types, as you can see here. For sweet cherry, with a hypothetical 50 centimeter rooting zone, we were going to estimate available water storage capacity values to be between 5 centimeters for coarse textured sandy soil and 10 centimeters for a finer textured silt loam. We can use soil moisture potential to determine if water availability to roots is becoming restricted. There are several technologies available, including electrical resistance blocks, such as watermarks, and various kinds of tensiometers, all of which can be used in automated systems. This is a new kind of tensiometer, which I'll discuss in a little bit more detail in the next slide, which has a far greater range than the typical barometer type tensiometers that we see here. Until recently, soil moisture potential measurements have been limited to soil moisture potentials between 0 and 2 minus 0.2 megapascals for granular matrix sensors such as watermark, or between 0 and minus 0.1 megapascals for tensiometers. But there is now a new type of rugged soil moisture potential sensor, the Terrace 21, which will provide soil water potential measurements down to minus 1.0 megapascals. So this is almost close to the permanent wilting point that has been defined for medium and fine textured soils. Most sensors will work for perennial fruit crops, although watermarks are not recommended for very coarse soils. There are two major technologies now used for measuring soil moisture content: time domain reflectometry, TDR, and capacitance probes. Both can be fully automated, although TDR tends to be more expensive. An example of an automated TDR trace is shown, indicating water content changes in response to daily scheduled irrigation in a sandy loam soil. There are a couple of things to note. Firstly, there is a difference in the value for the two different irrigation types being monitored. Values are higher for microsprinkler than for drip. Both probes are located at the same distance from the emitter. Placement is an important issue for soil moisture sensors and needs to consider the plant root zone and the water spread. Secondly, soil moisture is kept within a narrow range for both systems, and neither is increasing or decreasing over time, suggesting that irrigation is being applied to meet requirements in both cases. Most systems on the market are capacitance probes. These can be installed manually at desired soil depths and often come with other sensors associated with them, temperature and electrical conductivity, or EC, being the usual ones. There are also some systems that come with probes that are integrated into a one unit that can measure at a range of depths. These systems usually are supported by an irrigation provider, and in this case, we see such a system, which is for the Enviroscan irrigation provider. When scheduling irrigation using soil moisture measurements, we need to have trigger values to initiate and end irrigation, and in some cases, have measurements at different depths. These can be directly linked to a controller, or with fully automated web-based services, these may interpret the values for you. A simple example with tensiometer follows, which illustrates this principle. Tensiometers, for those who haven't seen a manual tensiometer for a while, this is what it looks like. Frequently use center bars as the measure of soil moisture potential. Note that the values are now positive. 0 is a saturated soil and 100 is a dry soil. In this example, water applications are initiated when readings reach 15 to 30 centibars, depending on soil type, and are stopped when readings reach 10 to 25 centibars. Note the very narrow range of readings, which occurs because we are looking at soil moisture ranges for micro irrigation systems such as daily drip, microjet, and micro sprinkler. To schedule a micro irrigation system based on these readings, again, these are ones that operate on a 1 to 3 day cycle. We maintain the desired moisture level in the soil by adjusting the runtime or increasing the frequency. It's much easier to adjust the runtime, particularly if your system is designed to meet peak demand for any one zone. So you can change that zone by changing the runtime to give the desired water quantity. If you have a fully integrated automated system, that runtime will be adjusted for you. A range of sensors then, the type we've shown, these are all various soil monitoring, moisture monitoring sensors, can be linked to various kinds of data loggers. And these can be data loggers such as this one, Camel Scientific, which can actually switch the valves on and off. So it's a direct wire to data logger to wire to valve. Or you could have a wireless system where you have a wire to a post like this, or a data logger like this, situated in the field that can transmit a signal to the cloud, to a cell phone, maybe directly to an irrigation controller that has some sort of programming in it. You can get information back from the cloud to the irrigation controller, particularly if the data are interpreted by an irrigation service provider, or back to the irrigator, who can also control the on and off switching of the valves. So the whole point of irrigation scheduling is to meet plant demand and to conserve water, as illustrated in this graph. What we can see here is that if we irrigate at one level more or less throughout the season, we over-irrigate at some times, we might miss peak demand, which is very important mid-season. but the potential water savings are great when water requirements are scheduled to meet plant demand. Other sensors are often used to improve irrigation management. Weather data sensors are used to estimate evapotranspiration, and water is applied to replace the volume previously used. Alternatively, ET data can be used with soil moisture data to calculate a water balance for scheduling purposes. Plant sensors can be used to estimate things like transpiration. This is a sap flow measure, or plant stress. These are leaf temperature sensors, and these can also be included in the mix for controlling irrigation systems. Remote sensing technology is also being deployed to assess spatial variability in plant stress and in soil water supply. One of the greatest challenges in precision water management is spatial variability. How to measure it? Do we need many sensors? And how to irrigate appropriately in response? At the moment, drop tube center pivot systems linked to soil moisture monitoring are the most commonly used systems to overcome soil moisture variability. But these are not suitable for tree fruit production. And really, the holy grail of precision water management is to find ways of meeting this unequal demand. Excuse me. And unequal supply in response to differing soil moisture content. So there are several automated multi-sensor systems on the market which often need a service provider to integrate the data to provide irrigation system control. Information can be fed back directly to a controller or the irrigator. I have just used an example of one such a system here, but there are many on the market. I just happen to like the picture. We have used simple two-sensor fully automated irrigation systems in our research projects. In this example, Skeena on GI6 were planted in a replant orchard with two types of irrigation system, drip and small radius microsprinkler. Irrigation was scheduled using an estimate of ET from an electronic atmometer and a data logger programmed with crop coefficient curves. The data logger switched the irrigation system on and off. Soil moisture was monitored hourly with automated TDR probes over a soil depth of 0 to 30 centimeters. The probes were located at a 20 centimeter lateral distance from the emitter. Soil moisture measurements were used to back up ET-based scheduling. In this case, microsprinkler soil moisture was consistently lower than drip soil moisture. This had consequences for early growth and yield and indicated that in this soil, either more frequent or longer applications of irrigation may have been warranted. In summary, effective irrigation management depends on well-engineered and efficient systems and is enhanced by irrigation scheduling to meet plant demand. Efficient scheduling requires monitoring of system soil moisture status. Soil moisture potential and soil moisture content can be used as triggers for irrigation. Sensors for soil moisture, plant water status, and evaporative demand can be used to operate fully automated irrigation systems. Thank you for your attention, and if you require more information on this topic, here are two publications that may be of use.